Hi, my name is Lakeland Bailey, and this is my final project for Computer Science 452, and the title is Pollinating Flowers with Particle Swarm Optimization. So, for my goal, I wanted to create an animation in Blender where bees come out of a hive and then they fly around and pollinate flowers and then return to that hive. And I wanted to give the bees the intelligence to do this using particle swarm optimization, and I'll get to that in a second. So, in terms of the bee behavior, we'll start with basic movement. So, for their basic movement, I just added the product of the velocity unit vector and their speed to the position each frame. So, the velocity unit vector is more so a direction vector because the speed is constant for all bees at all times. And the velocity is essentially in meters per frame because I don't really work with seconds here, I work by frame. I added some invisible boundaries that were just coded into the position algorithm that prevent the bees from going out of the flower patch. I implemented some functionality to make the bees always rotate to face the direction they're moving in 3D space. And I gave the bees a maximum turning radius of 30 degrees just to contribute to some natural movement and swarming around flowers instead of them moving in very blocky formats. So, in terms of how I implemented particle swarm optimization, particle swarm optimization involves solving a problem using particles that communicate with one another. That's a very high level definition of it. And in this case, the particles are bees. This type of equation or this type of application was derived from instances in biology where animals are moving around in a large body together, but they're only communicating with adjacent animals. Example would be bird murmuration, any kind of bee swarming, schools of fish, things like that. So this involves tracking a personal best and global best position, and these positions are worked into this equation here. So each time I insert keyframes for a new frame, I update the velocity using this particle swarm optimization equation. So what this does is here, there's a inertia weight. So this inertia weight is applied to the previous velocity. So a higher weight means more of the previous velocity is maintained. A lower weight obviously means more of the previous velocity is neglected. So inertia kind of just decides how much the bees want to keep moving in the same direction. And then this first product we've got here is we've got the personal best, or I'm sorry, the cognitive weight applied to this function. So the cognitive weight, that decides how much emphasis or how much the bees care about the personal best that they've found. And so that is multiplied by the difference between the personal best and their current position. So the C coefficient here, and this applies to this C2 coefficient over here as well, these coefficients are just random values. They're just a random value between 0 and 1, and this was applied just to simulate some of the randomness associated with biology. Over here, we have the R2 coefficient. This is the social weight. So this is the weight that's applied to the best social position they found, which is really the global best position. So this S best here is referencing the global best, and that social weight, which is a value between 0 and 1, is applied to the difference between the global best position and the current position. And then finally, when this new velocity is calculated, it's added to the current position to produce the new position for the frame. So for pollination, bees use particle swarm optimization to find and pollinate the flowers. They do this by moving around in a swarm and kind of dropping off some bees at flowers. And the reason they're dropping them off is bees will attach to flowers, and only 5 bees can be attached to a flower at a time. I didn't want the entire swarm of bees swarming around a flower for the entirety of the time until it's pollinated. Instead, I wanted the bees to move around and kind of deposit other bees at the flower so those bees can focus on pollinating that flower while the other bees move to other flowers. So if a flower already has 5 bees attached to it, then the bees will ignore that flower and they'll just move on. So the bees will iterate the flower's pollination counter. Any of the bees that are attached to a flower will iterate its pollination counter each frame until it reaches the pollination threshold, which means it's fully pollinated. I calculated the pollination threshold using the product of the frame rate and minimum pollination time and max nearby bees. The reason I did this was I wanted to set it up to where I could easily specify minimum pollination time, in this case 12 seconds, and it would take at least that long to pollinate a flower. The reason I say minimum pollination time is this calculation here is, the only way a flower will be pollinated in 12 seconds is if 5 bees are circulating it constantly throughout that entire time. So there have to be 5 bees attached for it to be pollinated in 12 seconds, which is how that pollination threshold is calculated. So assuming there were 5 nearby bees, so assuming there were 5 bees attached to a flower, it would only take 12 seconds based on this calculation. So moving on, so behavior stages. So there's 3 stages in this animation. The first stage is leaving the hive. This is just where the bees leave the hive on a constant trajectory and don't look for any flowers yet. Then the swarming stage occurs. This is when bees look for and pollinate flowers. And finally, they return to hive. So I set a frame remainder, based on the maximum distance a bee could travel across the flower patch. I used that value to create a frame remainder, which the way the program works is when there's only that many frames left, it'll transition all the bees to the returning to hive stage so that they'll all get back to the hive in time before the animation ends. So the way I use Python scripting. So I use 3 scripts here: generate bees and flowers, clear bees and flowers, and generate keyframes. So the generate bees and flowers script builds off of the default bee and flower. It generates 50 more flowers and 200 more bees, and it creates a new material for each pod child of the flower, which is the circular disc in between the petals, to allow color changes on specific pods for pollination. If all of the pods use the same material, then changing the color on one would change the color on all of them. So I had to create separate materials for each of them. And then this script also makes sure flowers and bees are evenly spaced. So let's go ahead and take a look at the script on GitHub. So the main function of the script is duplicate hierarchy. So this will take an object such as a bee, and it will duplicate all of its children. So this is kind of what's happening here. And if the child is the pod, then it will add the new material for that pod and set its base color to blue, which is what all pods start at. That means the flower's not pollinated. Right here, I have the is too close function. This just checks if an object is too close to any of the other objects based on the minimum distance. I have a place objects function. This will call the duplicate hierarchy on function for as many objects as I wanted to duplicate. And I made sure these functions all worked for both flowers and bees so I could use the same function. So at the bottom, all I do in this script basically is just get the foundational bee, get the foundational flower. These are the default bee and flower. And then I duplicate the flower 50 times and I duplicate the bee 200 times. This would create a total of 51 flowers and a total of 201 bees. For the bees, I start them off at least 2 meters away from one another. And for the flowers, I start them off at least 10 meters away from one another. This doesn't really matter for the bees, however, because as soon as the animation starts, they all get put into the hive. So this value isn't as relevant. I just use it in the beginning for some basic testing. So moving on to the next script, generate keyframe script. So this is the general body of the animation. So in this script, I generate all of the animation data for each of the bees and the flowers. The only animation for the flowers being their pod changing from blue to yellow when they become pollinated. So this script will clear all of the previous animation for each of the bees and flowers, and then it'll calculate bee movement and behavior on each frame based on the algorithm, and then it'll set the position for each of the bees for each frame, and it'll set the flower pods to the correct color on every frame. This script also handles the bee behavior transitions. It tells the bees when to transition from leaving the hive to swarming and when to transition from swarming to returning to the hive. So let's take a look at this script real quick. So there's quite a few behavioral defaults or behavioral factors that I have declared up here. Some of the notable ones are frame count. This just decides how many frames are calculated. Frame step, this is how many frames we move forward in the loop. I just go through every frame. Bee speed is just set to 1. But these are the primary parameters right here. So we've got the cognition range. This is the range in which bees can detect flowers. The social range is the range in which bees can detect other bees. Here's the cognition weight and the social weight. I just kept these even because I wanted to keep the behavior very natural and standard. However, I did want to put them higher than the inertia because I wanted the bees to prioritize more what they're learning about the nearby bees and flowers than their initial direction. And there's a couple of other factors here that I experimented with to adjust the behavior. A lot of these I kind of just set to 1 or to a negligible value because I decided they didn't really benefit the animation much. But I did keep them in here in case I ever wanted to experiment with them again. So this is a primary factor right here though. It's just the bee position bounds. This just decides the minimum and maximum values for their position for X, Y, and Z axes. And then here are those parameters that I mentioned previously: max nearby bees, minimum pollination time, frame rate, and then the calculation for values associated with that. And here I've got the max turning radius, things like that. So I've got some helper functions here. I've got this random velocity function. This just generates a random velocity unit vector. I've got flower count and bee count here. These global variables are just kept to keep a running ID of each flower and bee as I create them. So just to help out with some development and some code quality, I created this base object. Both the bee class and the flower class are children of this base object. So it just comes with some nice functions, like its constructor takes the object and the ID and it initializes those. It initializes a child cache for when this find child function is called. That just kind of speeds up performance a little bit. It has this clear animation data function. This just allows the clearing of the animation data for an object. Children just returns a list of the children. And like mentioned previously, the find child will just find a child with the given prefix within the hierarchy. So if I wanted to find the pod of a specific flower, I would call find child and I would just pass pod as the prefix and it would find that pod. Set color, this only applies to objects that have a node for their color, the principled BSDF node. And the only objects I applied that to in this entire animation were the pods so that I could change their color. So this function is only used for the pods. And then finally, I have a distance function. This is just a really generic distance function. It allows me to get the distance between 2 points. It's very important for this functionality. So the bee class is the most complicated class here. So at the beginning, I initialize some values. I set the rotation to 0. I iterate the bee count so that I can, use that value to set the ID and whatnot. And then I just do some general initialization. I clear previous animation data. I reset the personal best, the global best. I set a random velocity that's kind of aiming down so that they come down from the hive. I set is attached to false, action to leaving hive, and return to hive to false. So transition action will just transition. It will make the necessary value changes to transition the bee from a different action. So if it's currently leaving the hive, it'll set it to swarming. If it's currently swarming, it'll set it to returning to the hive. The update function will call all the necessary functions to update the bee's position based on its current action. If it's swarming, it'll need to pollinate nearby flowers and detect nearby bees and update the personal best and global best associated with those. If it's returning to hive, all it has to do is keep moving forward. If it's still returning to the hive, if it's in the hive, which is what I checked for here, I just set it to return. And this will basically just prevent any more movement from happening for that bee, just to improve performance a little bit on bees that have already returned to the hive. And then the functions that are always called in the update is, unless the bees already returned to the hive, is calculate position, handle boundaries, and then I set the new location. So calculate position will update the position based off of all of the different factors like the existing velocity, the global best if there's a global best position, and the personal best if there is a personal best position. The handle boundaries function will just redirect the bee if it's hitting one of the 3D boundaries that are set for it. And then finally, I just insert a keyframe for its location, and then I call redirect, which just rotates it based on the correct direction using a quaternion down here. So this just sets it to the direction it's supposed to be facing based on where it's moving, and it inserts a keyframe for it. So this is the handle boundaries function. It did what I mentioned previously. The calculate position function, it'll check. It first just does the initial part of the particle swarm optimization equation by just setting the new velocity equal to the current velocity times inertia. Because of the fact that I use 1 as inertia, this just basically means setting the new velocity to the current velocity. And then if there is a personal best flower set, it'll add the cognitive component to that. If there's a global best flower set, it'll add the social component to that value. If there is a max turning radius, I run this if statement just because I'm keeping all of this very parameterized so that I can experiment further in the future if I would like. So if there's a max turning radius, I do all of that. I make sure that the new velocity isn't moving in a direction that's exceeding that max turning radius. So there's just some editing of that stuff here. And then finally, once the new velocity is calculated, I set the current velocity to the new velocity and I update the position with I add to the position the product of the velocity and the bee speed. So reset personal best just sets some values to their default. Set is attached to false, set personal best to infinity, personal best flower to none, and previous personal best flower to none. This previous personal best attribute is only kept to know when a bee has switched from another flower to a new flower so that it can detach from the previous flower and reattach to the new flower. Reset global best just sets the global best flower and the global best to similar values up here, and it sets is attached to false in case it wasn't already. Reset motive only resets the personal best, and then it sets the velocity to a random velocity. This is because I wanted to preserve the global best if they had stopped aiming towards a particular flower. So in this pollinate nearby flowers functions, essentially what happens is I look for the nearest flower within the cognition range, and if the distance between the bee and that flower is better than the current flower position, it will try to attach to that flower and it'll detach from the previous flower if necessary and all of that. If it's both attached to the flower and the flower is not pollinated yet, it'll pollinate the flower down here. Otherwise, it'll reset its motive and try to find a new flower. And then finally, if its target flower becomes pollinated or it reaches max capacity and the current bee is not attached to it, it'll reset the motive there as well. The detect nearby bees function is a lot simpler. It just finds the nearest bee within cognition or within the social range, and then it takes the best value of the bee's personal best or its global best. So if the bee is a really good personal best, it'll take that value from that bee. Otherwise, it'll take its global best so that they can all follow in a swarm. And then if that new value is better than its current global best, it'll set that to the bee's global best, and it'll handle pollination of its global best here. Like if it's not attached to that flower and that flower becomes pollinated, it'll reset the global best. So essentially, at a high level, the detect nearby bees function updates the global best, and the pollinate nearby flowers functions updates the personal best, and that ends up working into the particle swarm optimization equation. And then I have this flower class here. This class is a lot simpler. It just kind of regulates the color of the flower, and it also keeps track of the total number of pollinations. So each time pollinate is called on this flower by a bee, If it's not pollinated already, it'll iterate the pollination count and then set itself to pollinated if it has exceeded or reached its pollination threshold. And depollinate will just set the flower to not pollinated. And then finally, the update function just figures out the color that the flower should be based on its pollination, yellow if pollinated, blue otherwise, and it finds its child pod and then sets that child to the correct color. Or its pod child, not its child pod. This clear animation data helper function here just clears all of the animation data for the entire scene. I just go ahead and call this here in case I did not call the clear bees and function or the clear bees and flower script. But yeah, and then here is basically the staging of the animation. So I get all the bees by instantiating all of the objects with a name that starts with B, and I do the same with flowers. And then I loop through each frame. If the frame is less than the initial pause frames, then I don't do anything. I just added a little pause in the beginning of the animation for when it zooms in, none of the bees will come out of the hive yet. And you'll notice that when we get to the animation. And otherwise, if we're past that, I loop through each bee and I update the bee. If we have exceeded the start swarming frame and the bee is not currently swarming, then I'll transition the bee's action. Otherwise, if the frames remaining is less than or equal to the return to hive frame remainder and the bee is not currently returning to hive, I transition its action again so that it'll start returning to the hive. And finally, I update all of the flowers down here. So that is the generate keyframe script. Moving on to the clear bees and flowers script, I won't spend much time on this one. All it does is cleans up all of the duplicated bees and all the duplicated flowers. It does not remove the original bee and the original flower. So this was just for some cleanup when I wanted to reposition all the bees or just do kind of a wipe of all of the duplicated bees and rebuild them. Flowers as well. Now, so we've reached the animation stage. So in order to create this animation, I first created the primary objects. I created the bee right here, created a pollinated flower, an unpollinated flower. Well, this is the same object, but it just shows an example of each. And then here I have my tree model and my hive model. So for the animation process, I essentially added the grass floor, just the basic plan on the bottom. I created the bee and flower models. I created and duplicated the tree and spread it evenly throughout the scene, but I left a large space for the flower patch. I created the hive and I attached it to a tree that hangs over the flower patch. And then I created and I ran my scripts to add all the animation. And then I added the animation for the camera movement and then I rendered the animation. So of course that doesn't include a lot of the debugging for the scripts and different stuff like that, but that's a high level explanation of how the animation process went. So now we've reached the animation video.